Hey y'all, welcome back. Tonight's homework, we're focusing in on infinite limits and limit laws. So not only are we going to go through and formalize the different properties of limits that there are, but we're also going to take a look at some limits that involve non-removable discontinuities. In particular, we're going to find the limits where x approaches a vertical asymptote. So let's jump right in. First of all, we've got two graphs. This first one on the left here is a graph of f, and the one on the right is a graph of g. They're both piecewise functions, and so let's see if we can't make some sense out of these limit questions. The first one says the limit as x approaches 2 of f of x plus g of x. Well, I'm going to rewrite it as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. Now, after you get kind of the hang of these properties of limits, you can kind of leave off this first step and just go straight to the next step. There really isn't much else to say about this, but it is important to understand how these properties work. So let's go ahead and evaluate each one of these. I'm actually going to change the color of this one just to stay consistent with how I circled them. So the limit as x approaches 2 of g of x, I think it'll just be easier to identify which one I'm actually talking about. So the limit as x approaches 2 of f of x, let's take a look and see what's happening when x gets closer and closer to 2. The left-hand limit is 2, the right-hand limit is 2. So in both cases, the limit is 2, and so therefore we say the limit is defined and it is 2. We're going to look at the same thing for the old g of x. As x approaches 2, well, it's actually continuous as x approaches 2. There's no break here. There's no discontinuity, so that limit is simply negative 1. So 2 minus 1 equals 1. For number 2, it's going to be kind of the same idea here, where we have the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x. The limit as x approaches 1, let me erase all my little markings up here, is going to be, let's take a look. So from the left, we're approaching 1. From the right, we're approaching 1. So that limit is just 1. I'm taking a look at g. We do have a discontinuity here. This is a non-removable discontinuity. It is not a hole. This is a jump discontinuity. We'll get in a lot more about classifying different kinds of discontinuities next time. But the point here is that the left-hand limit equals 2, where the right-hand limit equals 0. And since those two limits are not the same, this limit doesn't exist, which means the overall limit is not going to exist. For number 3, we've got the product of these two limits. So we have the limit as x approaches 0 of f of x plus the limit as x approaches 0 of g of x. Oh, I'm sorry, that's not plus, that should be times. You're multiplying these together, not adding them. There we go. So the limit as x approaches 0 for f of x, well, f of x is continuous at x equals 0. There's no break here. There's no discontinuity here. It looks like these both are pointing to 0. So we have 0 times something. So as long as this other one's defined, it's just going to be 0. Taking a look at the g of x, we can see that from the left and from the right of 0, it looks like it's actually a little bit above 1, but I'm just going to call it 1 because it's not really clearly defined. It's a little ambiguous. It does look like it's a tad over 1, but actually it really doesn't matter because anything times 0 is just going to be 0. Number 4. Here we're dividing two limits. Okay, this is going to be the limit as x approaches negative 1 of f of x divided by the limit as x approaches negative 1 of g of x. Well, the limit as x approaches negative 1, let's go back to the graph up here. As x approaches negative 1 from the left and from the right, we are approaching what is that, negative 1 divided by, let's take a look at g, when x is getting close to negative 1. Oh, we're getting close to 0. Ooh, yeah, so this is going to be undefined. We cannot divide by 0. Unfortunately, we can't do it. This is going to be, does not exist. This next one, we've got this kind of weird notation here, f squared of x. Basically, that just means that f is going to be multiplied by itself. So this is going to equal 3 times the limit as x approaches 2 of f of x. Let's make that, let's turn that red so we can stay consistent with our coloring here. We'll color scheme. Not 1, but 2. And we are going to square this. So whatever this equals, we are just going to multiply it by itself. So we got 3 times, looking back up at f of x, did we already find the limit? Yeah, so we already found that. At this point, it looks like we're starting to repeat some limit questions here. We can see that we've already calculated the limit as x approaches 2. For f of x, over here, it is 2. But you can look back at the graph if you don't catch on to that. So this is going to be 2 squared. So our final answer here is going to be 3 times 4 is 12. Number 6, we've got the limit as x approaches 1 of this square root deal that's happening here. So let's see what we've got. As x approaches 1, f of x is getting closer and closer to 1. We've already answered that before. So this is going to be the square root of 3 plus 1, which equals 2. Okay, there's that first part. Notice here on the last question, I kind of just am starting to skip the first step that I did on most of these where I'm citing the limit property. You don't necessarily need to do that once you get the hang of this, but it's also not bad to write it either, I suppose. Let's go on to the next problem. There we go. Okay. All right. For the following problems, we've got the limit as x approaches negative 2 of f of x is 2, and the limit as x approaches negative 2 of g of x is negative 3. All right. These should be pretty easy. All these limits are going to negative 2, so we're really just going to be replacing the functions with their values here, or the limits with their values. So with this one, we've got 5 times the limit as x approaches negative 2 of g of x, which is negative 3. So 5 times negative 3 is going to be negative 15. For number 8, the limit of f of x as x approaches negative 2 is 2. And for g of x is negative 3. So that sum is negative 1. For 9, okay, so here, as x approaches negative 2, this x squared is going to get closer to 4. So we've got 7 plus negative 2 squared times the limit as x approaches negative 2 for f of x, which is 2. So we got 4 times 2 is 8. 8 plus 7 is 15. Now we've got the limit as x approaches negative 2 of f of x over negative 3 times g of x. So this is going to be 2 divided by negative 3 times negative 3, which will be, 2/9. For number 11, it says, for x is greater than or equal to 0, the horizontal line y equals 2 is an asymptote, that is a horizontal asymptote, for the graph of the function f. Which of the following statements must be true? So all we know is that on the right-hand side of 0, we've got an asymptote at y equals 2. All right, so this function could be doing all kinds of different weird things, but at the end of the graph, we're going to be approaching it either from above or below, or we could even have some oscillating behavior as long as the amplitude is going to 0. So we've got a lot of little options here. You could have anything else like to the left of that where we're not in the end of behavior. You know, everything over here, really anything could go here. So let's see what must be true. The first one says f of x does not equal 2 for all those values. Well, that does not have to be true. Okay, you could have a graph where you're crossing that horizontal asymptote even infinitely many times. If your asymptote is 2, okay, so let's say here's 2. Here's your graph. You could have a function that does something like this. Okay, so it might equal 2 sometimes. So we know it's not going to be A. B says the limit as x approaches infinity must be 2. Well, yeah, for x is greater than 0, the horizontal line is an asymptote for the graph. That's exactly what this means. So yeah, B must be true. C, f of 0 equals 2. Well, that could be true, but it also could not be true. I mean, just take a look at that graph I did for A. We can see f of 0 is definitely not positive 2, but it still is going to, in the long term, approach y equals 2. So that doesn't have to happen, although it could happen. F of 2 is undefined. That could happen. You might have a hole here. Doesn't have to happen. So yeah, that's not going to be our answer either. And finally, the limit as x approaches 2 is infinity. That would mean we have like a vertical asymptote at 2. That could happen, but it doesn't have to happen. So that doesn't have to be our answer either. So for sure, our answer is B. All right, going back to some mixed limit practice here. So we're going to practice our algebra here. This first one, I'm going to multiply by the conjugate of both the numerator and the denominator. So that's going to be root x plus 3 minus 4 over root x plus 3 minus 4. This is a little bit of a review from previous lessons. We want to multiply that out. So I'm going to have x plus 1 times root x plus 3 minus 4 all over x plus 3 minus 16. Oh, wait a minute. I got kind of carried away here, didn't I? You don't have to do any of that. You do. Wow. I'm making more work for myself here. You don't have to do any of that. I take all that back. You could, I suppose, do that, but it's not really going to get you anywhere because you're not going to have any factors that cancel out because there's no hole at x equals 6. My goodness. Yeah, that was my first reaction, but my first reaction should have been, hey, let's just try direct substitution here. So we get 6 plus 1 over root 6 plus 3 plus 4. I guarantee you that's going to happen to a couple of y'all too. You're just going to get so in the habit of, hey, there's going to be a hole there. There's going to be a hole there when, sometimes there's not a hole there. There is no removable discontinuity here. So yeah, we just get 7 over square root of 9 is 3. 3 plus 4 is 7. So this just equals 1. That one is a lot easier than I thought at first. Okay, number 13, this is a limit at infinity. This was our very first lesson of the year. And as x goes to negative infinity, we want to say this function, since it's a rational function, is going to approach a horizontal asymptote. And since the denominator is growing the fastest, okay, this is going to approach y equals 0. Not y, we're just going to say equals 0. There's no y here. The horizontal asymptote is y equals 0, but the value of the limit is 0. Number 14, the limit of pi squared. Pi squared is just a constant. There's no variable here. This is just a graph that basically does this at pi squared, right? So it doesn't really, x could be going to 0, x could be going to 1, x could be going to pi, x could be going to anything because x, there's no x here, there's no variable. So this is just going to go straight to pi squared. 15, another rational function and a limit at infinity. So we're thinking about those horizontal asymptotes, and this one has a horizontal asymptote at -4/5 because those cubic units or cubic terms are the fastest growing terms, and we see one in the numerator and the denominator. So this is just going to equal -4/5. Number 16. Ooh, this is going to look a little familiar after Unit 1, but we can still handle this. We want the limit as h approaches 0 for this function. Can't just do direct substitution here, so we are going to have to do a little bit of algebraic manipulation here. And again, this problem right here, this is probably unless I'm forgetting something, the first time or the first hint of rate of change. And you don't know it yet, but this little equation here is describing the slope of some function. So let's go ahead and simplify here. We got 9 minus 9 is 0, and then we can factor out an h in the numerator. So we've got h times h plus 3 over h. And so we get, let's bring it down a little bit, the limit as h approaches 0 of h plus 3, which is 3. Number 17. Number 17. We cannot plug in 1. Now we cannot plug in 1 here. It's going to make the denominator 0. It does not make the numerator 0, though. So 1 makes the denominator 0, but it makes the numerator 4. Okay? Since that numerator is not 0, that means we have a vertical asymptote. And so the way we're going to handle these vertical asymptote problems is we're just going to try to get as close to 1 as possible. So let's pick a value and see, well, are we going to positive infinity or are we going to negative infinity on either side? So let's pick a number like 0.99. So test x equals 0.99. Okay, so right to the left of 1. All right, so if I'm going to put 0.99 into this function, I'm going to get 0.99 squared plus 3 over the square root of 0.99 minus 1. Now, I don't really care exactly what this equals. I'm not going to use a calculator here. I just care if it's positive or negative. We can see clearly that the numerator is positive, and the square root of 1 is 1. So the square root of 0.99 has to be smaller than 1. So that means some number smaller than 1 minus 1 is going to be negative. So to the left, we're going to negative infinity. In other words, the limit as x approaches 1 from the left of this function is negative infinity. So a better way to say it is probably that it doesn't exist because it goes to negative infinity, but that's the basic idea. Now let's test something like 1.01, something just to the right of 1. So we got 1.01 squared plus 3 over the square root of 1.01 minus 1. Okay, numerator is obviously positive. The square root of 1.01 is going to be bigger than 1, so the denominator is going to be positive. So that means that the right-hand limit is not going to exist because the value of the function is approaching. Got that square root symbol. It's kind of hanging a little far out there. Is going to approach positive infinity. So notice here that the left and the right hand limits do not equal. So we're going to say that does not exist. Number 18. Looks like we may luck out with another direct substitution problem. Let's see if this plays out nicely. Let's see, 2 times 1 squared minus 11 times 1 plus 5. over 6 times 1. Yeah, I think this is going to work out pretty good. So we got 2 minus 11 plus 5 over 6 minus 3. Try to take this slow, make sure my arithmetic's good. We got 7 minus 11 is going to be negative 4 over 3, so that's going to be our limit. Number 19, we've got some fractions we got to take care of. So let's try to find a common denominator in the numerator. So I'm going to multiply the left-hand fraction by x over x and the right-hand fraction by x plus h over x plus h. So this will equal the limit as h approaches 0 of x over x times x plus h minus x plus h. So minus x minus h. And all that will be over h. So dividing two fractions would be equivalent to multiplying by the reciprocal. So I'm going to have x minus x is 0. So we have negative h over x times x plus h times 1 over h. And we can see here that our h's are going to reduce to 1. So now we can go ahead and just plug in 0 into h. Negative 1 over, x times x is going to be negative 1 over x squared. Oh, this is kind of interesting. So this is going to be a variable. Yeah, this is not going to be a constant. This limit is going to be in terms of x. So I should have mentioned something at the beginning where I noticed that I have both h and x in there, and just be careful that we're sending h to 0, not x. Number 20, we're sending x to 0 here. So let's see what happens when we send x to 0. Well, first of all, let's factor out an x. Okay, we've got x times e to the negative 2x plus 1 over x times x plus 1. Reduce those x's, and I think we could just probably plug in 0 after that. So that's going to be e to the negative, well, that's going to be e to the first. That's just e on top. You plug in 0 into x, negative 2 times 0 is 0, plus 1 is 1. And then if we plug in 0 on the bottom, it's just over 1. So yeah, this is just going to equal Euler's number e. Number 21. Can't substitute in 4, but what we can do is factor that numerator and hope that we can get rid of a 4, an x minus 4. If not, then we've got a vertical asymptote. So the two factors of the numerator are going to be x minus 3 and x minus 4. So we do get that cancellation happening here. So we have the limit as x approaches 4 of x minus 3. Substituting in 4 is going to give me 1. Number 22. Plugging in 7 is not going to work, unfortunately. And we do have a hole here because 7 also makes the numerator 0. So we're going to have to multiply by the conjugate here. Root x plus 2 plus 3 over root x plus 2 plus 3. So this is going to equal the limit as x approaches 7 of x plus 2 minus 9, which is going to give us that x minus 7 we're looking for, times root x plus 2 plus 3. Just to save a little space here, hopefully you can see that this x plus 2 minus 9 is the same as x minus 7. So those will reduce to 1. And then we could plug in 7 into x. So 1 over the square root of 7 plus 2 is 9. So 3 and 3 is going to be 6. So 1/6. For 23, once again, we can't plug in 9 there. That's okay. It's kind of a weird one. Yeah. So, 9's not going to make the numerator 0. So we have a vertical asymptote. So So let's see what's happening as we get closer and closer to 9. So we're going to test, I guess, something like 8.9. 8.99, we get even closer. And so we've got the square root of 8.99 over 8.99 minus 9 to the fourth. This is going to equal a positive number over a positive number. Raising something to the fourth power is always going to be positive. So actually, we don't even really need to do any testing here, because no matter what we plug in here, we're going to be positive. Okay, so we know the limit as x approaches 9 from the left does not exist because it goes to infinity. And if we test, let's say like 9.01, we're going to see the same behavior, because when we raise that thing to the fourth power, that denominator, it's going to be positive. So this is also going to be positive. So the limit as x approaches 9 from the top, or from the right rather, this function is positive infinity. Now these are the same, so it is okay, even though technically the limit doesn't exist, we can say the limit as x approaches 9 as a whole is going to infinity. Now if you say does not exist, I'll take that too. All right, we got two more problems here. Let's knock this out. Number 24, we've got a quartic divided by x minus 2. Now let's just verify that this is divided by, well, I guess if it's not, then we probably have bigger issues. But let's assume for the moment that this is going to be divisible by x minus 2, meaning 2, we do have a whole at x equals 2, in which case we're going to try to rewrite this as the limit as x approaches 2 of x minus 2 times some cubic over x minus 2. Now, I thought it was kind of interesting in class when I said, what do you guys like to do, synthetic or long division? Some people said synthetic, but I think most people, the majority who spoke up, said long division, which really surprised me because synthetic division goes a lot faster. So I'm going to use synthetic division here because I'm interested in getting this done as quickly as I can and still getting it right. If you want to do long division, you are more than welcome. So let's see, we've got 1, negative 11, 21, negative 1, negative 10 as our coefficients of the polynomial that we're trying to divide. Bring down the 1. 1 times 2 is 2. Minus 11 is be negative 9. Times 2 is negative 18. Plus 21 is going to be 3. Times 2 is 6. 6 minus 1 is 5. 5 times 2 is 10. And look at that, we do get we get no remainder, which is what we want. And those are going to be the coefficients of this other factor. X cubed minus 9x squared plus 3x plus 5. Now we can reduce those two factors to 1. And we could just plug in 2. So this is going to equal 2 cubed minus 9 times 2 squared plus 3 times 2 plus 5, which is going to be 8. Let's see, 4 times 9 is 36 plus 6 plus 5. I hope my arithmetic's good here. I'm trying to do this without a calculator just because, you're not going to have one on the test or anything. So 11 and 8 is 19 minus 36. So let's do a little quick arithmetic out here. 36 minus 19, carry the 1. 16 minus 9 is going to be, 7. 2 minus 1 is, so 17. Yeah, I should have been able to get that without that, but that's okay. So we got negative 17. Assuming my arithmetic's good there, I might go back and double check that. Number 25. This is going to be the last problem of the homework, it looks like. We want to find the value of the limit as y goes to negative 2. And we can see this is a piecewise function where the breakpoint's at negative 2. So what we need to do is we need to test both the left and the right hand limits and see if they are equal. So for the left hand limit, we are going to plug in 2, or -2, into the left hand function here, because that's where y is less than -2. So -2 squared plus 5, that's 4 and 5 is 9. And then calculating the right hand limit, we're going to substitute in -2 into the bottom piece. So 1 minus 3 times -2, that's going to be 1 plus 6 is 7. So this limit doesn't exist because the two one-sided limits are not equal. And that about wraps it up for tonight's homework. Y'all, thanks for watching, and y'all have a great day.